So today we'll pick up where we left off last time briefly. I investigated this a little bit more, and let's take a look at that graph we were trying to make before. Okay. So this is just the code from last time. And we have our coronavirus data sets. So I'll run through really quickly, loading in the libraries, loading in the data set, changing the date to a date format, adding in the daily cases and daily deaths, and then splitting that FIPS number right into the state and county FIPS numbers that we need so that we can merge with the census data, load in the census data, and then merge that with the coronavirus data set. Okay. So last time, at the very end of class, we wanted to do something where we could think about essentially doing a display where you have two lines. So you have both the daily cases and the daily deaths. That is, in addition to the faceting method that we showed, one way that I can take sort of multiple dimensions to kind of display, right? So you can split it into multiple lines. That's an extra dimension. I can do multiple colors. That's another dimension. I can do, you know, for lines, I can do things like dotted lines, dashed lines. That's another dimension. Depending on the plotting type, you can do things like the size of the line, size of dots. Those are all extra sort of dimensions that you can fold in so that you can show multiple variables into a single plot. And then it's kind of up to you to decide, you know, how digestible, right, that visualization looks. And that's something that I think will come with practice. So if you recall last time, I tried to do this thing basically where I had my ggplot, and then because we were short of time, I decided to do this thing where I could display both of those dimensions with two separate geom lines. But I usually don't really recommend this way of doing it, because to properly leverage the power of ggplot, usually actually what you want to do is to get all those dimensions, the multiple dimensions for a single variable, into a single column. Okay, this is the whole point of the melt function. So let's actually take a quick moment to implement it that way instead of what I had done. So I'm going to make this table into a long format as opposed to kind of what we have as a semi-wide format right now. And what I mean by that is we currently have this table, right? And you have things like the date, the state, the county, and so on. So these ones are all fine, but I also have cases deaths and daily cases and daily deaths. And these are all separate columns. And instead, I want to combine these into a single column. So we're going to call that count and then type. So then in the type, I can have my cases or my deaths with the corresponding counts here. And this suddenly becomes a single dimension. And I can specify things in ggplot using this column. Okay. So we will use our melt function again. I'll just put in my COVID DT here. And then I have to give the ID variables. Again, the ID variables are all the things that you don't want to get melted together. So in this case, that's going to be everything else. Okay, and then here I wanted the variable name to be type and the value name to be count. So I just say variable.name equals type. And this part is optional. If you don't do this, it'll just name it by the default variable names when it does a melt. So this will be called variable, this would be called value. If you don't do these last two inputs into the function. Okay, so I run this. Yeah, that's fine, I think. So covid.dt.long. Actually, let me open it over here. It should be a little bit easier to see. Yeah, okay. And so now what we have, instead of a cases column, a deaths column, a daily cases, and a daily deaths, you just have a single column with types and an indicator for which one it is. Okay, so let's get to the punchline here. Why did I do that? Let's do a quick, simple example first. So covid.dt.long. I'll put the data here. Okay, and then in our aesthetics, now I can do something like date, x equals date, y equals count. Okay, and so basically the idea is I'm going to make a plot here, and I want, say I want 2 lines, 1 line of my daily cases and a different line for daily deaths. So all you have to do is color equals type. And then everything else stays the same. Let's add in some labels. Xlab is date, and Ylab is count. And we'll do our theme here. Okay, this would get really crazy if I did everything. So I'm just gonna do YOLO county. So county equals YOLO. Okay. So if I run this, what's going to happen? How many lines will get produced? Any guesses? 1 line, 2 lines, 3 lines, 4 lines? So as I've explained it, you should have 1 separate line for each color. Okay. How many? So each type will have its own color. How many types do we have? So we have cases, and we also should have deaths, right? And then we have daily cases and daily deaths, right? Okay, and we can check that, okay? If we're not sure about that, I can look at the values, unique, covid.dt.long, $type. Okay, so this should give me all the unique values under that column. So there's 4 of them. Okay. So what's cases and deaths again? Cumulative. So if I plot these guys on the same axes, well, okay, why don't we see what happens? The cumulative one kind of swamps out everything else, right? So we don't want to do that. So in here, I'm just going to add in an extra filter, although you can see, right, that there are sort of 4 different lines. YOLO and type in, and I'm just going to have the cases.daily and deaths.daily. Okay, so then it looks something like that. Does anyone recall how to pop that out in RStudio? I don't actually know how to do that. Yeah.
There's an export button.
No, can you like pop it out as a separate window? Zoom? Ah, here we go. Perfect. Thank you. Okay, that'll be easier to do plots in the future. So this looks something like here. Still, like you're not going to see very many deaths. There haven't been that many in Yolo County, but a fair number of cases. Okay, so that's how you can show sort of multiple lines, and more importantly, sort of arranging the data in this way allows you to view kind of multiple dimensions, right? So in this, we have the dimensions of cases versus deaths, and I could add in, right, an additional dimension if I wanted to add more like locations. Let's say I do Sacramento in here. Let's do this. Is this still the for? Oh, no. Okay, this is the updated one. Okay. So I added in, as I was describing, there are like a variety of ways that I can put in an extra dimension into the graphic. So I have color, the different types will be broken out by different colors, and then the different counties are going to be broken out by different line types. So here we have a solid line indicating Sacramento and a dotted line indicating Yolo County. So you can see there's like a little red dotted line here that's kind of hard to see. And then in the solid red is Sacramento. And then you have daily cases and daily deaths. Red being the cases and green being the deaths. Okay. So in this case, I might look at this and say, oh, that's really hard to see. Maybe I prefer to show that dimension a different way. And we can revert to what we had shown before. So with the facet as an alternative way of showing that extra dimension. And I'm going to do the scales free Y to allow the facets to work on different axes. And then that's going to show this plot here. And in this case, now we can see, more clearly sort of the distinction between these, and then they're operating on different axes as well. So there's been, right, I can easily see the peak cases. There's been like 10 times as much in Sacramento compared to YOLO. Okay, any questions about this? Yeah.
Is there a way to because the depths are like really zero, although they're not zero, you can only kind of perceive them in this plot. Is it possible to do a secondary axis or break up the axis?
Yeah. Okay, we'll get into my spiel about secondary axes. So yes, you can. You can put something on a secondary axis, and sometimes there are legitimate reasons to do so, but my general thoughts about secondary axes is that you should not really ever do them. Maybe that's a bit of a sort of strong statement, but let me kind of discuss the principle of that. Okay, so we'll kind of end our discussion about visualizations here. So I'm going to pull up the board. Okay. Blank display and so we've got our X, our Y, and our Z. Okay, so let's say you want to have two things. plotted on here with a secondary axis. We actually do it like this, so we can be clear about what colors correspond to which line. So I want you guys to pay attention to this when you see this in the future. If you're, whether it's in, you know, the Economist, or if it's in somebody's study or something like that, in like a proper paper, anytime you see two axes, you might be seeing something like this. Okay, well, like this. And usually what they're showing is maybe some opposing trend, right? Or maybe some corresponding trend, right? Okay, so let me ask you guys. What would you describe as the relationship between my y and my z, given this visualization between this blue and my red lines?
An ambiguous relationship.
Okay. Great, ambiguous. So basically, like, maybe not that strong of a relationship. Okay, great. What about now? Would you say that there's more of a relationship between these two now? Maybe. They're inversely related, and we'll say the first one maybe not so related. Okay. What if I told you that those two were the same plot? So the problem here, and this is the thing that I want you guys to pay attention to when you see these types of plots, is whether or not there is like a physical relationship between y and z, okay? And if there isn't, which I would say 99.9% of the time there isn't, I am allowed to manipulate my axes here because there's no corresponding relationship between this number and here. And so I can artificially change the scale of this to show a pattern, right here. And I can just say A and B, right? So it's the exact same plot, but I can choose how I want to scale this to demonstrate a point that may or may not be real. Okay, so yeah, like, what are some examples of this off the top of my head? Yeah, so maybe you have, I don't know, like GDP and population, okay? And then you want to show the relationship between GDP and population. So you do this thing where you have one line of how GDP changes over time, and you have another line that shows how population changes over time. But population and GDP are not fundamentally connected in any way. So I can change the scale of my axes against each other to either magnify slopes of lines or to diminish, right, the slopes of the lines. So, okay. That's not to say that like secondary axes don't have their kind of time and place. There are legitimate examples of this, right? Like if you wanted to show like a temperature relationship, like Fahrenheit to like Kelvin. Okay, they're on really different axes. So if you had these lines, you know, they could look really different, but there's like a physical, you know, relationship. And so you can have some kind of change in the scale. But I will just give a word of caution for any time you see secondary axes or you're thinking about doing secondary axes, to be careful of things like this. Yeah.
So in a lot of like energy graphs, like
yeah.
TTP or something on the y-axis, like which is directly related to temperature most of the time. Like if you're doing that in Excel, usually the axis is set for you. But how could you can't really change.
So if there's a direct relationship between y and z, then it's okay.
Okay.
Yeah, but if not, then you can change the scale, right?
Okay.
Yeah. Okay, one more thing. I guess as long as we're getting into pet peeves about graphs, I'll do another one really quick. Okay, let me think. Okay, so percent of time graphs oh wait, percent of time, how does this work again? Y axis not starting at 0 is deceptive. Okay. This axis is percentage of the time that not starting your y-axis at 0 is deceptive. So it looks like it's half the time, but in reality, we started at 99% here. So if we started at 0, this graph would look slightly different, right? It would look like that. Another sort of pet peeve of mine, this is a way to manipulate your visualization again in usually a disingenuous way. This is, again, another sort of rule of thumb and something to just watch out for. There is a time and a place to do manipulation of your axes in certain instances, but usually I would frown upon this type of thing. Oftentimes you'll see people trying to sort of magnify trends, which again can be legitimate, but yeah, be careful of this sort of thing. Does this make sense to everyone? Okay. Great. Okay, and with that, let's get on to our material for the day. Okay, let's look at this equation, y equals beta x. So this is kind of the form that we've so far looked at. It's purely linear, and that allows for us to interpret relationships between x and y that we deem are linear. And sort of throughout the rest of the course, we're going to start to stray a little bit more from what I'll describe as kind of the functional form, which is the functional relationship, right, between these, which right now we're assuming is linear, and we'll kind of depart from that little by little. So in this case, how would I interpret the relationship between x and my y? With just this equation? Anyone? If I change x by 1, how would my y change? Yes. So y will either increase or decrease by beta. Yes. In fact, it'll just change by beta. And if beta is negative, if the value of beta is negative, the y will go down. And then if beta is positive, y will go up. So perfect. Okay, so then, so to get that change, right, this would be delta y is equal to beta times delta x. So the whole idea here is as x goes up by 1, y will go up by beta, or down if it's negative, right? But the change is basically looking like something like this. So what I'm going to introduce here is technically still all in the linear form, but it allows for some kind of transformations that are really common in this area that still uses a linear regression without sort of having to revert to some of the more complex things that we'll talk about in a little bit. So this relationship will sometimes be called level-level. But oftentimes you can have, so linear relationships are actually not so common in the data, but exponential relationships are actually fairly common in sort of natural data. And so one of the things that you can do to keep it in this form is to do what's known as these log transformations, which will take exponential types of data and linearize it. So if you have something like this or something like this, it can transform this into here, and then you could just do run the regression again on the transform data to get that relationship. Okay, and so we'll look at this log dash level. So this would be something like the ln of y would be equal to beta x, like so. And essentially what this is doing is saying, oh, as x, you might do this type of thing because as x is changing, you might be observing some kind of like exponential change in y. So you can log that to linearize it, and then you could just run a linear regression again. Super, super common to see this type of thing happening. And that's why there are these kind of shortcuts to not use sort of different types of regression to look at this. You just do this linearization method, and this is still totally fine and legitimate. Does anyone know how to interpret this in the same way that or the analogous way, I should say, that we're doing here? Okay, so in this case, the way that you can interpret this is, so a percent change in y is equal to 100 beta times my change in x. So basically, the idea is as x increases by 1, y will increase by 100 times beta percent. So x goes up by 1, y goes up by beta percent, essentially. So if beta here in this equation is, say this is 0.3. So as x goes up by 1, the value of y will increase by 30%. Okay. Has anyone heard of this before? No. Okay. It's a little odd. Why does this work out? So this is like super common in economics. You might see things like this to do measures of like elasticity and that sort of thing. It's usually log-log. We'll get to that for elasticity, but it's very common to see this type of relationship. But I should caution. So especially for people who get into econometrics and sort of the field of regression analysis in econ, because this is really common. This type of thing, this thing that I'm describing here, is sort of most accurate for marginal changes. So small changes in your x. So let me describe why we can do, so hopefully this part is intuitive. Let me describe why you're allowed to do something like this. So log of 1.01 is actually approximately 0.00995. Okay, and so that's about 0.01. So it's this relationship that basically allows this to sort of mathematically work out, this simplification in interpretation. Okay, so you can see how a 1% change in the value of this corresponds to a 0.01 sort of real value. So that would be your beta on the other side. Okay. So thankfully, we have this type of thing, and it allows you to do a simple interpretation when you have log level models, analogous in the way where we say x goes up by 1, y goes up by beta. Here we can say x goes up by 1, y goes up by beta percent. Okay. So maybe you can guess what's coming next. We have level log. So this is y equals beta log of x. What do you guys think this looks like? Same type of thing, yes. Yes, okay, absolutely.
Yeah, like when it's 100 beta percent, my head is like beta. 100 times beta and like the second percentage of it, is it coming back to the beta?
Wait. I'm not quite sure what you mean.
Because you initially said beta is 0.3, and if you put that 0.3, you put that 100 into 0.3%, it will
0.3. Right, it is, wouldn't it be just the beta then?
Oh.
Like if we have a percentage and 100.
Yeah. Yes. Yeah, that's right. Hang on, I'll always get this mixed up. So you have to multiply. Okay, wait, I can look here. Okay. That's right. It would be changed by that percentage. So you don't have to multiply by 100. Is that right? I'm getting myself mixed up here. Okay, hang on. So let's do this. So if x, okay, let's say this value is 0.3 and x goes up by 1. So then the delta would be 0.3 times 1, which would be 0.3 on this side. And then each one of these is a percentage difference. So then y would go up by 30%. Yeah. The key is that in this interpretation, the percentage, right? So, okay, so this is actually correct. So it's the same thing, right? You're right, it's the same thing, but the key thing is that the value of y isn't changing by 0.3, it's changing by like a factor of 0.3. Does that make sense? So 30% and 0.3 is the same thing, but it's not
Going up by 0.3, going up by 0.3, 30%.
yeah. So yeah, just to be sort of abundantly clear here, like let's say the value of y is 10 and our beta is 0.3. In the level, when x goes up by 1, y will go to 10.3, right? Whereas here, when x goes up by 1, y will go to 13. Does that make sense? Yeah. So yeah, the 0.3, if you kind of interpret that as the factor change, then it's the same. But the main difference is by saying there's a percentage change. That's the main difference. All right, am I confusing anybody? Okay, so hopefully this 10 to 10.3 and 10 to 13 will be clear. Okay, so we can leverage this same type of relationship over here in the level log. So here, the idea is if x goes up by not 1, but 1%, then y goes up by beta over 100. Okay. So you are leveraging the same sort of relationship to allow you to do this interpretation. And in this case, as you change x not by a set amount, but by a percentage amount here, then y will change by the flat beta over 100. Yeah. Sure, yes. Okay. So this is 0.3 and this is 10. Okay, so x goes up by 1%, and so y goes up by beta over 100. So this would go to 10.003. Great. Last one, log. Okay. Y is equal to, log I'm kind of interchanging between log and ln. So I'll just say for the purposes of now and all of the rest of the course, log refers to the natural log. Unless I explicitly write log base 10, whenever I write log, just interpret that as natural log. I can't think of me ever using base 10 log in this class, so we'll see if I eat my words. Okay, so log y is equal to beta times log x. Is anyone seeing a pattern here? What do you guys think is going to happen? How should we interpret this? Come on, I've laid it out for you. Yes.
I want to say that X is going to go up by 1% and Y is going to go up by B.
Yes. Almost.
Okay. Almost.
X goes up by 1%. Y goes up by beta %. This is the most common one that you'll see, log. This is the sort of one that like economists use to derive elasticities. So a % change in X leads to a % change in Y via this beta relationship. So this beta would represent the elasticity between X and Y. Okay. So that is kind of our first mild dive into other functional forms, which we still, in this case, leverage the linear regression to do, because these transformations with logs linearize your data. And so that allows for you to maintain linear relationships between your parameters. Okay, so we're obviously going to get way more into this later on in the course. But for now, let's move on to talk about some other tools to think about as you do some of these regressions. So if you can recall in the first, well, not first day of class, but first day of us talking about regressions, I drew some points here. And then I asked a bunch of people to come up and draw some lines, right? But I intentionally made it a little bit tricky by adding in, right, a couple points like this that are a little bit farther out, okay? So you might have heard of this before, right? People call these outliers. So what are some ways we can think about these outliers? Okay, so raise your hand if you think that's an outlier. Couple people. Okay, so for the people who thought that was an outlier, how about this guy over here? Still? Yay, nay? I see some, everyone's convinced it's not an outlier anymore. Okay, well, so I don't really know, right? Wouldn't it be good if we had some kind of like quantitative way of figuring out if it was an outlier? So we'll look at a couple different ways of doing exactly that. So actually this exact concept, which I wasn't meaning to do, where I'm starting to shift this down, relates to the first measurement that I'll talk about. So this is known as leverage. And it really is kind of like what the word describes. It's like, if you think of a lever, right? So the whole idea is, okay, I have this point, and if I ran a regression, right, that point is going to pull the line up. Okay. And if you lowered that point and you continue to lower that point, that's going to influence my line down a little bit more and more. Okay. So the idea here is, how much would the predicted value change if the observation shifted 1 unit in the y direction? Okay. So just as I was describing, I moved this down a little bit, and how would the predicted value for this x change on the line? So this is something where the way that it's measured, it will always be between 0 and 1. So the sort of formal definition of the point, of the leverage for a specific point, looks something like this. So the idea here is the delta yi drops by 1, and the line changes slightly. And so as a result of dropping the x a little bit, so you will have 2 points here, a y hat 1 and a y hat 2. And the difference between those divided by this difference, by that sort of marginal change, will be your leverage value. Okay. And you can do that calculation for every single point in here, right? And so the points that have the largest leverage are the ones that are influencing your plot the most. Okay. There is an alternative way, quantitative way of measuring the effect of individual points, and that is known as influence. This is also referred to as the Cook's distance. So this is the effect of deleting the point. So you can imagine here, instead of moving my y down by a little bit, I just delete it entirely and see how the line changes. And so if it's a point within a lot of the sort of other cluster of data points, you can imagine the line won't change very much. But if it's like really far away and you delete that point, and you would have sort of a larger effect. So both influence and leverage, basically the larger the size, the more likely it is that you could classify it as an outlier. So nomenclature is usually DI for Cook's distance. And this looks something like this. Sum of J equals 1, Yj. So this is the fit without point I. And this is number of parameters or coefficients. So for a particular point di, you do the sum of the squared error, right? For the predicted value minus the predicted value without that point in your regression. And you divide it by your MSE. Okay, so let's jump into R and see how we do this. Okay. All right. Let's see. So we are going to wait for the screen to turn on. Hello. Okay, great. Okay, so we've done this like 17 million times already. So hopefully you guys can all see what's going on. We're randomly making 100 x's. We're going to make our random error term. Same as we've been doing in a bunch of our lectures. Great. Okay, and now what I'm going to do is I'm going to add a single outlier. So I'm going to add amongst our 100 data points a 101st data point where x is equal to 100 and y is equal to 20. And let's run all this stuff. Okay. And let's have a look at the plots. Great. All right, man, does that look like an outlier or what? I'm great at making outliers. All right, so we got this like 1 point way the heck out there. So let's take a look at these two examples. So the first thing is actually, I'm going to run my regression. And the reason why I do that is actually both examples rely on essentially doing this kind of regression, right? We have the predicted values, right? And so in both of them, which means you're essentially trying to run some regressions anyway. So we're gonna, the functions will use this as a way to understand what the relationship is predefined. So we'll see what happens in just a moment. Okay, so there's our example model. Let's actually take a quick look at what this says in the summary, right? We know again that the true value, okay, come on. We know that the true value of beta is 0.5. Let's see, because of the outlier, what do we have going on here? Yeah, okay, so we have, instead of 0.5, it's 0.42. And in fact, the standard error is 0.016. So to get a true slope like this, compared to probably what's looking something like this, you would be what, like 4 or 5 standard deviations away from 0.5 or standard errors. That's a pretty large amount. That's a pretty low probability. So, okay, let's take a look at the leverage. Leverage, you use hat, like so. Hat is the function to get the leverage value. You need to put your example model into a sort of matrix form to feed it the information about the model. And let's see what this is. So let me type leverage here. Whoa, okay, we got a bunch of values here. And remember, maybe you were expecting the leverage for that 1 point, but remember the leverage is for every point in the data set. So let me quickly show what this looks like. Okay. So here, these are for every point in our data set, the leverage. And then that's the leverage of our outlier. So in this case, you can kind of easily tell, but let's talk a little bit more sort of philosophically about what an outlier is and what and sort of how you can deal with it. So with leverage, there's a kind of rule of thumb. If you're above some kind of threshold value, we consider that an outlier. So when you're doing the analysis, the context, I think, is really important for like what you should do when you find an outlier. A lot of people just throw them away, which can be a legitimate approach. But you have to ask yourself sometimes like, okay, I see an outlier. Is that the product of like something faulty in the data? Is something like being misrepresented? Or is the outlier showing like a true data point about some kind of like relationship, right? And those two things could dictate how and what you should do to deal with that outlier, about whether or not you should drop it out, whether you should leave it in the model and still interpret it as such, and make some qualitative discussion about like, okay, here's the results. We have these weird data points, but they're legitimate data points, so we don't want to just throw them away, right? So the leverage and the Cook's distance are both tools to help you discern that certain points are sort of more influential in your model, right? But just because they're an outlier doesn't mean that you should discard them. Okay, let's look at, actually, let me plot X versus leverage. Yeah, you'll see something like this. So this is a noticeable feature of leverage. All right, how does a lever work over here? Let me, right? It's sort of balancing on a pendulum here. So the closer you are to kind of the center of mass, I guess, the less leverage that you have, right? So that if I put some amount of force over here, right, you get more torque if you're farther away. In the same way you can see here, right? So one of the things that will affect the size of the leverage is kind of where you are relative to the center of mass for your X values. So just be cautioned that you will naturally have variation in your leverage purely, part of it is purely due to kind of where you are relative to your X's, okay? That's why there's like this threshold thing. If you're above like, I always thought it was 0.2, but maybe it was 0.1. That's like considered territory where you might be having an outlier. Okay. And then Cook's distance is just Cook's dot distance of your model. And I can plot that. And we can see what that looks like over here. This makes a lot of sense, right? Eliminating any of the regular points in our plot, with all the points like like that, that's not really going to change your model very much. But taking out that one point will. So yeah, and I'll note that for leverage, everything's always between 0 and 1. You have a standardized frame of reference. And there's this like standard threshold value. That's not the same in the Cook's distance. This depends on the context of your data and the context of your model. Okay. So in this case, it's like 12, right? But it could be really different depending on the data that you have. Yeah, so for threshold, or sorry, for leverage, the threshold I think is like 0.1 to 0.15. I'll put that in the more detailed notes. But for Cook's distance, there isn't a clear threshold because that value depends on the data in the model. Great. Any other questions or confusions? Yes.
Is there, like, as the number of data points increases, are all these values gonna go up? Like, what I meant to say, the influence of each of the points is gonna be higher?
As the number of, yes, it will, yeah. You can tell that mathematically. Who remembers the equation for mean squared error? So MSE has a n in the denominator. Wait. Yes. Is this going to be the opposite of what I just said? So n. Yeah. N gets moved to the denominator and then n goes down. Okay. My my intuition is the same as yours, which is influence should go up as there are fewer points. But mathematically, I'm getting turned around here. Let me think about that and get back to you, because this is not as intuitive as I thought. I would venture to guess that it will still go down, but let me figure out why this is the case with this thing. Let me make a note of that really quick. Okay. Great. Let's go back to whiteboard stuff. Okay, so multiple regression. We are just going to continue to sort of layer on complexity into what we've done so far. So this is extension of simple linear regression to predict the value of a variable based on the value of 2 or more other variables. Okay. This is kind of like the next logical step in our modeling. So yi is equal to beta xi plus epsilon I. So now we're going to go to yi equals beta 1 times x1 I plus beta 2 times x2 I plus dot dot dot. Beta n minus 1 x n minus 1 I plus beta n x n I plus. Okay. So the idea here is that I'm starting to basically say, well, y might be influenced by more than one variable. And so we're going to start to sort of control for these other variables. Okay. This is where we start getting kind of tricky in terms of doing things purely in terms of visualization, because the added sort of dimensionality becomes harder and harder to visualize, right? Because in our sort of original, we have something like this, x, y. And okay, pretty easy to do, but even as soon as we get into 3 dimensions, let's say this is my y, this is my x1, this is my x2. Okay, I will attempt to draw this. So let's say the like larger points they are, the like closer they are to you. Okay, so we'll have something like this, something like this. Okay. So then you are now, it's still linear, all linear relationships in each plane. Okay. This might look something like this. And then something like that. So instead of a line, you have like a plane that extends in all directions, right? Okay, who wants to draw the plot for x1, x2, x3? It's gonna get pretty tricky. You could actually do it with like colors and that sort of thing, but it rapidly becomes totally kind of infeasible to kind of visualize. And so if you think back to a lot of the tools that we've already talked about, we can already think about how you can extend things like the residuals, for example, which is always going to be in 2 dimensions because it's just y hat and the residuals. That's going to let you do diagnostics on some of these things without having to do these like super complex visualizations. Okay. The last bit that we'll talk about is okay, I'm going to do this next time. We're just going to look at one more thing so that we can have time to look at this in R. So it's going to talk about dummy and categorical variables, but we'll just start with that next time. Okay, so back to here. I can turn on the display. Great. Okay. So we are going to do multiple variable regressions. So now we're going to do a similar type of thing, but we're going to have multiple points here. We'll have x1, x2. We'll even have x3. And we'll even have x4. Okay, so this time I'm generating 4 different vectors, x1, x2, x3, x4, all from a random uniform distribution of 100 points. x1 and x2 are going to be between 0 and 50. x2 and x4 are going to be between 0 and 100. Okay. We're going to have deviation multi. This will be the same type of thing here. Okay, and now we're going to define y dot multi. And this will be 0.5 times x1 plus 2 times x2 plus deviation multi. Oh. Okay, so in this case, again, what you guys would see if you had a data set would be y multi x1, x2, x3, x4. You are not privy to this information. But as the sort of omnipotent person, I know that the true relationship between my y and all of these x's is that it is a function of 0.5 x1 and plus 2 times x2. That's the true relationship. We don't know that. And so you might have this data set and you say, hey, let me just go ahead and test all of these guys in the regression. Okay. And let's see what happens. Actually, let me plot all of these guys first. Okay, this is just making it so that I can do a 2x2 window for the plots. And I'm going to copy and paste this a couple times. And I'll just change this to x2, x3, x4. Okay. Oop. Hit zoom. All right. So here is a slight word of caution. I just did a visualization of x1 versus y, x2 versus y, x3 versus y. We know the true relationship, right? Y is related to both x1 and x2. But if you just looked at the plot, you might think, oh, okay, I've determined like most of it, it's all going to be coming from x2, right? Like very clearly I can see this relationship. However, we do know that x1 also plays a role in what y is, but it's getting swamped by the fact that that's 2x, right? It's 2 times x2, whereas this is just 0.5 times x1. So this relationship gets swamped out by the larger one. And it actually looks pretty similar to these random guys, right? So just looking at the plots is not necessarily good enough to be able to sort of dismiss it as a variable, okay? It's still very useful to do this type of thing, right? Because then you can say, well, I'm not going to rule out x1, x3, or x4, but I have a pretty good idea that x2 is going to be important. Okay, so again, the idea is just to layer on as much as we can with all the tools that we have to try and come up with the sort of best model. Let's go ahead and run this y multi on x1 plus x2 plus x3 plus x4. Okay, and summary example model 2. Okay, this is the power of your regression tool, right? Just throwing in that data, and it's like, you can't trick me. I see 0.5, 2, and basically 0 for both of these. So running this linear regression, you know, for this artificial example, you know, admittedly artificial example, shows you that, you know, it is sort of very powerful in being able to pull out these relationships, especially if they're linear. If the true relationship is linear, that sort of functional form between your x and your y, this linear regression method, there is nothing that will beat it. Okay. We're going to get into sort of more complex sets of models where the relationship isn't linear, but this type of approach can still approximate it, but then we'll start to delve into these other sort of approaches that might do a better job, that are more generalized. But there are trade-offs in doing that. Part of the big reason for using linear models is its simplicity and the ease of the interpretability here. And that's why, like, whole fields of like econometrics is like built off of essentially this type of thing. Okay, and so hopefully this kind of showcases some of the power of the linear regression. All right. Any questions about this? Okay, great. Yes, I don't think we quite have enough time to kind of dive into the next topic. So I think I'm just going to hold off on that till next class. So we will end slightly early today. Yeah. And so as a quick reminder, the homeworks are due at the end of the day today. So make sure to get those in. And remember that you have to submit it, the R Markdown file and the compiled either HTML or PDF file from the R Markdown in the homework. Yes.
You want us to draw the table from number 1 in the homework in our Markdown?
So you can, yeah, so that would be most preferable. I did give some resources about doing tables in R Markdown, but if you're having trouble with doing that, you can write it out in text too. That's okay. Any other questions? Okay, great. Thanks everyone. I'll see you guys next week. Yes.
This has nothing to do with art, but last night you were talking about EV installation charges.
Yes. Okay, one sec. Let me stop recording.
Oh.